Hey guys, welcome back to this video on PyTorch. So in the previous video, we delved into the theory of transformers, and now we will we will look at an implementation of transformers in PyTorch. So again, this is just a code walkthrough. I'm not going to type any code. I'll just go over the PyTorch example on transformers. That's in their documentation page. All right. So this was the transformer model that we talked about. This is an old style of architecture which has both encoders and decoders. Modern transformers have either just encoders or just decoders. We'll see how to implement this. Now, PyTorch has a bunch of layers, and let me open some of them up, like multi-head attention. So we saw the attention mechanism. So instead of implementing that from scratch, um, so there's this torch.nn.multi-head attention layer that takes in the embedding dimensions, the number of heads, and then basically it does the whole um, multi-head attention operation. So basically, I think yeah, the number of head tells it like how many different attention blocks that you want. And let's look at an example. Yeah, so what it takes in the query key and value matrices and then performs attention mechanism and then gives you the attention output. So that's pretty much it about this. Let's look at what the attention output weights are. Let's see. Um, I see the attention output. Attention output weights are um, hmm, not sure. Maybe I'm forgetting something, but these are only needed if I turn on need weight equals true. So I'll have to revisit this. Maybe I'm zoning out on what these are. But this is the main thing that you need. You need the attention scores rather. So that's that. Now, um, now if you want to stack a bunch of encoder layers, so you have the transformer encoder that takes in the encoder layers. And what is an encoder layer? So encoder layer is basically the attention mechanism with the feed forward network. So it's made of the self attention and the feed forward network. So basically, let's say if I pass in the transformer encoder layer and the internal dimensions of my model are this and the number of heads are 8, it basically performs and I pass in a sequence with some batch and I basically get the computation out. Now, what it does is it internally computes it has internally it creates the multi-head attention layer because you can see it has the number of head parameters and so basically it's the whole block that you saw in the original image. So that's one good thing about PyTorch. It provides you these high-level APIs that basically do everything for you. So that's both good and bad. All right. So yeah, and then yeah, so we talked about encoder layers, and let's okay. Let us look at the implementation. So I have pulled out the implementation in PyTorch, so that we can play with it. And let's first look at the imports. So obviously math, tuple. Um, I don't know with what library this is. Then obviously functional is imported, and then the encoder and the encoder layer. So let me revisit the difference again. So encoder layer, um, right? It is made of self-attention and feed-forward network. So that's one stack. So what I mean by that, so this one stack is an encoder layer. Now, this layer stacked, or this one block is the encoder layer, which has the attention and the feed forward layer. Now, stacking this block multiple times is the transformer encoder, which stacks these encoder layer n number of times. So that's the only, so one is made of the other. All right, so we subclass from the NN module to create a transformer, and we call it transformer. The first thing we define is a position encoding layer. So um, hmm, let's look at this layer. Let me, or is it something that's internal defined here? Oh, no, no. The position encoding is this layer is defined here. So I'll come to that in a bit. So we talked about position encoding. So here you have the position encoding, and then we have a dropout factor and also the model size, or rather the internal representation size in the model. Then we create encoder layer, consists of transformer encoder layer, which has the size, the attention heads that you want, the hidden dimensions, and the dropout. And then this encoder takes this layer and repeats it n number of times. So this is the whole encoder block. And then um, so finally, we also have the embedding layer because that's what you want as well, the embedding that takes your tokens in, and a variable D model that tells you the embedding size of your model. And also we have a decoder, which is just a linear layer here. All right, so this indicates that this model is an encoder only model because we just have these encoder blocks, and the decoder is just finally the output of the encoder will be passed into a linear layer. So, and then the weights are initialized in a uniform manner. So that's that. Now let's look at the most important function, forward. So whenever I read a code, I look at the forward function because that tells you what the operation of the network. So that gives you an idea. All right, so let's say first I get some input, which is source, and then I get a mask as well. Why do we need mask? Mask is useful during training because that tells the network not to look at, so when training you get the whole sequence at a time, and mask tells the network not to look, so it's a diagonal matrix which tells the network not to look at subsequent words. You only want to look at the words that have already occurred to generate the next prediction. So this transformer is doing an NLP task of predicting the next word given the sequence of words. So that's why you need the mask. All right, so given the input, we first encode the input using uh, the encoder is the embedding layer. So we first get the embedding representation, normalized embedding representation by passing it through the embedding layer. Then we also pass it through we pass the same input through the position encoding layer. And then once you have the position encoding, that means now you have a numerical representation that also encodes the position. So then I pass it through the transformer encoder, which takes it through all the stacks of encoder blocks. And then whatever output I get, I pass it through the decoder, and then boom, I'm done. So what we have done is get the input embeddings, do the positional encoding, and then pass through n stacks, and then finally pass it through a dense layer here to get the output. All right, and these masks are generated by this function, and as you can see, it's a diagonal triangular, upper triangular. All right, let's look at the position layer. Um, so what it does is, let's look at its forward function. It takes in the input and then applies the position embedding, because position encoding is added on to your regular embeddings. And here you generate the position embedding depending on the dimension of your input and the length of your sequence using sines and cosines. So even numbers are added with sines and odd positions are added, excuse me, with cosines. So, and then here there's just a normalization. So this we discussed last time, but this just performs the positional embedding. All right, now we will look at the data. So in this example, they use the Wikitext2 dataset. So let me, I actually don't know what this dataset is. Well, let me run this and also this. So let's see what Wikitext2 is. And also open the PyTorch page for it. Um, all right, so Wikitext it's obviously language modeling, collection of 100 million tokens extracted from basically Wikipedia. Okay, and is there a quick way to see some samples? Let's see. Um, this link doesn't work. Let me search for some sample. Okay, so hopefully this. Oh, I see. So it's just Wikipedia pages. Um, hmm. Yeah, okay, so I can see Super Mario Land, gold dollar, and everything. These are just Wikipedia texts. All right, fair enough. Okay, so PyTorch has this torch text for datasets API that contains a bunch of datasets just like it has for ImageNet and I don't know if it or CFAR and MNIST. So we will make use of this API to obtain um, the Wikitext2 data. So language modeling, torch text.datasets.wikitext2, and all right, so that's all you need to type to get um, and then get the data set, and then you can split it into training and test using split. So I think we are good. Okay, let's go back to our code. And now in Wikitext, um, first of all, a couple of important things. The vocabulary object um, is built based on trained dataset and it's used to numericalize tokens into tensors. So basically, word tokens we will convert them into numeric representation. And unknown words are given by this tag. So given a 1D vector of sequential data, that means given, let's say, a sentence, um, we will we will construct a function, batchify, that will arrange the data into batch size columns. So let's look at this example, which is more instructive. Um, and why we are doing batching, because obviously parallel programming and all that jazz. Okay, so and yeah, so batching means model treats each in column independently. Now let's say my sequence was 26 letters, A to Z, and let's say I have to split this into 4 batches. So the way I would do it is like this. So that means 26 divided by 4, each sequence has length 6. So A, B, C, D, E, F, 6, 6, 6, and 6. So these are my 4 batches. So I've split my text into 4 parts and made sure that these are sequential or contiguous. All right, so let's look at the data, how we process the data. Okay, so basically from torch text, what I just showed you, we import wikitext2, we import the tokenizer, and also another vocabulary from iterator. So these are two things that I want to show you. Let's open the tokenizer. All right, so tokenizer basically, um, what it does is, let's say I have a tokenizer and I write a string. It will break the string down into individual bits, which are individual chunks, which are like this. You can now install TorchText using pip. So basically, break it down into words or whatever sequence that they have chosen. So our tokenizer would use basic English, so it'll break down English words into chunks like this. So that's what the tokenizer does. So that's tokenizer. So first we get our the train split of our wiki text. We get the tokenizer. Now let's look at this build vocabulary from iterator. Um, so let me open this. Is there any example? Oh, build vocabulary from iterator. Okay, so what it does is basically construct the vocabulary from your iterator. So let's say I had all my words were A to Z. So when I create a vocabulary, that means all my words would be made of only 26 letters, A to Z. So that's my vocabulary or of characters. So similarly, you need vocabulary of words. So each word would be assigned a token or a numerical representation. So that's the words your model can represent. So here, what's happening is basically we use the tokenizer on our training data and construct the vocabulary. So vocabulary would contain all the text in our data, um, and we set any unknown thing to be this to be represented by unc. So let me show you. I'll run this bit code, and I'll go over the other piece in a bit. But let me show you the vocabulary. Or rather, let me see it as well because I am not. Haven't used the. Okay. So vocab is a. Is there any way to see? Well, what my vocabularies are? Um, hmm, I don't. I mean, it seems like it's a module, but let's see if I can use it as a function. Pass in something. No. Hmm. Oh, let's look at its code. What its parameters are iterators, special. What are the methods that it has? Let's see. Okay, I can obviously use length. Um, oh, okay. Then let's try a word test. Okay, great. So this gives you the index of the word test, and this gives you the index of the word, say, sunny. So that's my vocabulary. So let's see how many words are in my vocabulary. That many words. Now, how did I know how to search for this? Was because I saw this dunda dunda get item. So that's the method. So yeah, so a vocabulary has been made that basically converts each words into numeric representations. All right, now um, what we do is, so there's a data process method that will, yeah. So what it does is given data, so given the data, um, and the data is coming from the wiki text, it will um, loop over it. So this is an iterator. That's why you can loop over it. So for every um, chunk, okay, let me go back to Wikitext2 and see what is the size that is pulled every time. Okay, batch size by default is 32 and the BPTT length is 35. So um, these are the sequence length that are pulled during each iteration. So let's say if I okay, let's see. Let me just quickly try this. I'll, for I in train iter print I, and then I'll just break. Um, okay, what happened there? Oh, okay. I think the first one was just blank. So you can see, well, oh, let me do an enumerate. If j is greater than 10, or if I is greater than 10, break, and I'm outputting. Okay, now I'll make it 1. I'll tell you what I did. Okay, so this is the text that is pulled each time. Let me do, let's see, is it, oh, the chunk sizes are different every time. So let me do print length of j. 30, hmm, 30, 694, 520, 574. Hmm. Each sample, okay, so this is grabbing samples from my Wikitext and each sample size is different. So, okay, well, that makes sense. Each article has different word length. So that's why we need to batchify it. Okay, so this is what I was trying to do just to see how the data is being read. So the data when you in the iterable is just a bunch of paragraphs at a time, I guess, because all of them are talking about this what Chronicles 2, Valkyria Chronicles 2, and then I'm getting a bunch of paragraphs at a time, or paragraph with a bunch of words at a time, sentences of words at a time. Okay, so I get this, and then basically I pass that into my vocabulary, and that creates this data object. So, all right, so at this point, I process, so basically then I convert that into strings of, or rather, string of numbers, because I use the vocabulary method on it, and then convert that into tensor. So here at this point, I would have my all my data in a numeric fashion. Um, okay, so that's good. Then basically I select my device if I have a GPU, CUDA, if not a GPU, CPU. Then we will divide our data into batches. Now, how we do that is given the data, we select the batch size. So this will divide my data into that many separate sequences. Just like here, A to Z was divided into 4 sequences. So here we will divide our data into 20 sequences. And how we do that is first figure out the size of the first dimension, and then just take the mod of it with the batch size, and then I will take that many elements in my data sequence and basically convert that into a column format. And the same thing, and then I pass it to GPU or CPU, whatever. So when I run this, let me show you how the final output looks like. So if I do train data, it's a tensor, and guess what's this dimension size? It would be 20 because that's my batch size. Just to check that out. Yeah, it's 20. Dimension 1 is your batch sequence. So I have 20 sequences, 20 batches of this being the sequence length. All right, and all of them are numbers as you just saw. Okay, great. So we have now attained, we have batched our data or batchified our data in this format. Now we need to so this is a separate batch that's like batches of sequences, and now we need to construct batches that will be fed into the neural network, and that's what we will see now. Okay, so now what you know from the previous session, transformers take in data in one go, so it will take the whole sequence in one go. Now we can't make our sequence long because attention mechanism is order n squared. So that's why we need to have a limited size. We can't fit in, um, you know, this length of sequence in one go. So we need to turn it down into smaller batches. Um, the collab is missing a picture here, so I'll go back to the original example and I'll show you like how we will batch our data. So now we will construct a function that first of all splits our data into input and target, and also creates batches for training the network. Now, language modeling is it's easy to get data because you can scrape internet like Wikipedia and whatnot, and to train you don't need targets because you can just train it on the next word in a sentence. So let's say the sentence was function to generate input and target sequence. I can make a lot of training samples from it. So let's say if I say function to generate, guess the next word. Then function to generate input, guess the next word, and so on. So I can make a lot of sequences out of it. So the same thing this function will do, which will subdivide our source data into chunks of length bptt. So let's say in this example, if our bptt, I don't know what does it stand for? Batch bptt value of 2. So that means our first batch, so let's say my sequence length is 2. So here my sequence would look like this. So this is the input sequence. So I'm taking only 2 at a time, AB, GH, MN. So these are my 4 sequences, and then I take them 2 at a time. And then the targets are, so what comes after A should be B, what comes after AB should be C. So those are my targets. So what comes after B is C, what comes after G is H, H after I. So sequence length is 2, number of batches are 4. That's how I will train my model. And the targets are basically the next letters or next words in our case. All right. So the way this function works is I define a BPT of 35, so 35 words in one go. So attention mechanism would be 35 squared. Basically, and then I need to have some kind of an iterator that keeps track of which sequence do I want, and then basically get the sequence length, which is the minimum of BPTT, and whatever's remaining. Then I basically just grab that much amount of data and I get all the 20 batches. So all the 4 sequences here. So same thing. And then um, basically return. Target is just one ahead, because that's the next word you want to guess at each iteration. And then you return the data and the target. So now we have created, so this function will construct batches of the data. Let's now create the model. The model basically has, okay, let me go back and run this. And now my model has the number of tokens is basically the length of my vocabulary. I chose an embedding dimension, hidden dimension, number of layers, number of heads, dropouts, and then construct the transformer model out of it. All right, finally, we have to write the training loop. Okay, so first we define a loss because this is language modeling. We're figuring out the right next word, so it's a cross entropy loss. Some learning rate scheduler, our optimizer, and then the train method. So we first set our model in the training mode because we want to worry about backpropagation and whatnot. Um, Variable to keep track of loss, and then basically the source mask, which generates my diagonal matrix of mask depending on the size of my sequence length. All right, so now I batch over my data in chunks of BPTT. So I will loop over my data in these chunks and right, sorry, my bad. So first of all, I figured out from the length of my data and the batch size, how many batches should there be. Then I loop over from zero. So wow. Okay, so I enumerate over this range, which is from 0 to the size of my like total sequence size in chunks of BPTT. So enumeration means batch. I would jump from 0 to BPTT to 2 times BPTT and so on, and batch would go to 1, 2, 3, 4. So once I have that, I get the data and targets using the get batch function, which I just talked about. And then we get our batch size. Then we just check for, hey, if it's the last batch size, we have to just clean it up a bit. Then just pass this data into my model, get the output, and then do compute the loss. Now we are computing the loss on the entire sequence because using this mask, we were giving each word like all the input came together and the output came together, and now we will compare the loss of each terms. So uh, this loss computes all the loss of the BPTT sequence in one go, and then you know put the optimizer to 0 grad backward and um, clipping, and then step towards that gradient. So that is pretty much it, the training loop. So now then some printing of how the training is going. I'll run it to just well to see how it does. But um, let me also talk about how it should be evaluated on. So let's say I will turn on the evaluation mode, and then now the total loss is 0, and then the same thing. Well, this is not no different because then we feed in the evaluation data without what it's just the same training step without the whole backpropagation nonsense. Well, not nonsense, but we don't need backpropagation here. So this is the training of my network, and here basically is where I train the network for 3 epochs and then uh, try it out on um, an evaluation set. So pretty straightforward. Let me close the collab. What helps is like a lot of effort went into putting the data into the right format for us to use it. Batchifying it, putting in the right format, and then the model was only the first quarter of the discussion. The model required 5 minutes to go over it because PyTorch has made it so easy because there are these transformer encoder layers, and the multi-attention layers that just take care of everything. So with these layers, you can do more fancier things. Now you can also do vision transformers because ultimately these only deal with matrices. So as long as you can put your data in a nice format, you can use these layers directly. So as with all the deep learning models, the data organization takes a lot of work, and the model itself is rather pretty straightforward. So at least I don't expect anyone to type this out and figure this out yourself. It's a good exercise. You should definitely do it at least once in your life. But my whole plan was to just go over this because this uses everything that we have kind of learned over the last in this series at least, and now so that I don't think it's hard to read this model, and it's a pretty straightforward model, and then we can figure out, how things have been implemented and so on. So um, this is like a practical session for our in our series where we've been, covering out very specialized topics and so on. So I hope you found this useful, and keep on keeping on. And I will keep on making some more videos on PyTorch and have to figure out what to do next. Pruning seems like a good direction to go. Their PyTorch's documentation has a lot of interesting examples. I don't know if vision transformer is a thing in their examples at least. I know vision transformer is a thing in PyTorch, but I don't know if it's in their examples. But anyway, I think this is enough for this video. It has gone long enough, and I will see you guys next time. All right, bye.